In this lecture, we will discuss reflection and refraction by the ionosphere. We have an atmosphere shell around the Earth and have different parts. Ionosphere is the part which is responsible for communication purpose. So it is very important section for communicating electromagnetic waves from one medium to one part place to another place. We will discuss about ionosphere and then about reflection and refraction in this lecture. This is the syllabus and we are almost the end of the syllabus, finishing this unit. Ionosphere has several layers, so we will get a brief idea about the layers, what is the process of functioning, a mechanism of refraction of our waves through ionosphere, and then necessary formulas. We all must be aware of the word ionosphere, made up of sphere of ions. Ionized part of Earth's upper atmosphere. This is about 60 km to 1000 km altitude. A region that includes the thermosphere, part of mesosphere and exosphere. What is ionosphere and that other details? If you want to go into detail, you can search elsewhere. Here we will take relevant information about various layers and how the transition takes place with this. As we know, the ionosphere is ionized by solar radiation. So when sun strike on this, electrons comes out and the system is ionized. This ionosphere plays a very important role in atmospheric electricity and forms the inner edge of magnetosphere. It has practical importance because, among other functions, it influences radio propagation to distant places of the earth. Yes, it is used to communicate the signals from one place to another place. The region below this ionosphere is called natural atmosphere or neutrosphere. Here you can see various layers: troposphere, stratosphere, mesosphere, and from after that mesosphere we have thermosphere, exosphere and ionosphere. So basically after mesosphere there is an ionosphere which is used for propagation purpose. Here on the right side is shown electron density is also shown, which shows that the electron density is also increasing from layer at the bottom to layer in the upper place. Initially increases, first increases and then decreases. As we already discussed, the ionosphere exists between 90 to 1000 km above the Earth's surface, and radiations from the sun ionize atoms and molecules here, liberating electron from molecules and creating a space of free electron and ions. Subjected to external electric field from a radio signal, these free ions will experience a force and be pushed into motion. However, Since the mass of the ion is much larger than mass of the electron, ionic motion are relatively small and may be ignored. That is why we observe some interesting results here. Here some layers are shown in the night and day. In the night, two layers are shown here, E and F, but in the daytime, DE and F1, F2. In the night, F layer is the only layer of significant ionization present, while the ionization in the E and D layer is extremely low in the night. During the day, however, D and E layer become much more heavily ionized, as does the F, which overlap additional weaker region of the ionization known as F1 layer. The F2 layer persists by day and night, and it is main region responsible for refraction and reflection. So this gives the idea. Now we will discuss each layer in detail one by one. First D, then E, then F1 and F2. But this gives a brief idea how the layers are formed and responsible for communication. D layer is the innermost layer, 16 kilometer or to 90 kilometer above the surface of Earth. Ionization here is due to Lyman series, alpha hydrogen radiation has a wavelength of 1 to 1.6 nanometer, ionizing nitric oxide. In addition, high solar activity can generate hard X-ray that ionize N2 and O2. Recombination rates are high in the D layer, so there are many more neutral air molecules than ions. Immediately they form and then recombine other. Medium frequency and the low frequency radio waves are significantly attenuated within this D. As the passing radio waves cause electron to move, which then collide with other molecules, giving their energy. Lower frequency experience great absorption. Why it happens? Because they move the electron further, leading to greater chance of collision. This is the main reason for absorption of HF radio waves, particularly at 10 MHz. Now, about 10 and below MHz, less absorption occur at higher frequency. This effect peaks noon, it is reduced at night due to decrease in D layer thickness. As we have discussed, the D layer may not exist in the night, so this effect will not be there. Only a smart off remain due to cosmic rays. Generally, this is used for AM broadcast band in the data. Next layer is E layer. This is the middle of layer from 90 to 150 km above the surface. Ionization due to soft X-ray and far infrared radiation are possible in this region. Ionization of molecular oxygen takes place here. Normally, at oblique incidence, this layer can only affect radio waves having frequency lower than 10 and may contribute to a bit of absorption on frequency above. So only all frequency above 10 will be absorbed. However, during intense sporadic events, the ES layer can reflect frequencies up to 50. The virtual structure of the E layer primarily determined by competing effect of ionization and recombination. At night, the E layer weakens because of primary source of ionization is no longer present. And so after sunset, an increase in height of the E maximum increase the range to which radio waves can travel by reflection. Another layer is also there, sporadic E layer, ES. This is characterized by a small thin cloud of intense ionization, which can support reflection of radio waves relatively up to 225 MHz. And this may last for few minutes to several hours. The next layer is observed on the above, that is F layer. The F layer or region also known as Appleton-Burnett layer, this extends from 150 to 500 km above the surface. And this is the layer with the highest electron density, as we also saw in the previous graph. This implies signal penetrating this layer will escape into space. If your signal move to this, then it will move to space. Electron production is dominated by extreme ultraviolet radiation ionizing oxygen. The F layer consists of one layer at night, but during the day, a secondary peak F1 often forms in the electron density profile. Because F2 layer remain by day and night, it is responsible for most skywave propagation of radio waves long distance frequency. Above F layer, the number of oxygen ion decreases and lighter ions such as hydrogen and helium become dominant. The region above the F layer peak and below the plasma sphere is called topside ionosphere. In this figure, it is shown that the free electron density of the order of 1000 to 1012 electrons per cubic centimeter are produced by ionization from the sun rays. And the layer of high intensity of electron are given special names called DEF. We have discussed this and we are summarizing. Now during the day, F is split into F1 F2 while D vanishes at night. The radio wave below 40 MHz are significantly affected by the ionosphere, primarily because radio waves in the frequency range are reflected by the ionosphere. The E and F layer are most important for this process. For frequencies beyond 40, the wave tend to penetrate through atmosphere versus being deflected. The major usefulness of the ionosphere is that reflection enables wave propagation over a larger distance than would be possible with line of sight or even atmospheric reflection effects. The important thing about this is from here we can check what frequency should be used for propagation. This is an interesting question. From where the reflection come from? The reflection from the ionosphere are actually produced by reflection as the wave propagates through the ionosphere. The ionosphere is a concentrated region, highly charged ions and electrons that collectively form an ionized gas or plasma. And this gas has a dielectric constant that is function of various parameters, including electron concentration and frequency of. Now this plasma region is responsible for reflections. You can see here a radio wave has been sent to the ionosphere, and the wave reflected from the system. It is entering here, then after that sometime it is exiting. The electric field produces a force on given electron and displaces it along a vector as shown in the left side figure. So electron move in the particular direction. The displacement of electron along with the path can be modeled into an equivalent situation when the original electron remains stationary and the equivalent electric dipole is added. Now, if there are n electron per unit volume displaced by R on average, then the volume polarization can be calculated and given in the next slide. Now, if we know the dipole moment and number of atoms there, then we can calculate polarization, which is equal to NER. It's called equation of motion for a single particle of mass m. Velocity v, which is equal to dr over dt. If it is acted, then this can be written out Vm into dv upon dt is equal to minus E. And the electron also experiences a frictional force when it collides with other. So the actual equation can now be modified here. This is your equation, and this equation is modified here as this. F is the electron collision frequency. If we rewrite the term, that you will get this term. Now for sinusoidal fields, we can rewrite equation in terms of phasor and replace d by dt with j omega. And you can write this equation like this as shown here. Me omega square r minus E minus j omega me upon r. And from here, on substituting the values, we can find out the value of polarization. Is shown here. Now we also always know the DE relation. D the displacement field, is the electric field, it is the polarization. T is equal to epsilon 0 E plus B. If we use the value of P polarization here, then we get the value they have. Then the effective relative dielectric constant of the plasma is epsilon R1 minus this. We have calculated using this formula, equating this formula. And from here we can also calculate plasma frequency, which is equal to Ne square upon Me epsilon 0. We see that in presence of electron collision, the dielectric constant can be done as like this: epsilon r is equal to 1 minus omega p square minus omega square, which is equal to 1 minus 81 n on f square. From this result, we can make several important observations, since the propagation constant A traveling in a plasma is epsilon over k0. Now we have three cases: frequency, omega, which is greater than omega p, the effective dielectric constant is less than unity. But propagation constant is real. Hence, the wave will be reflected by the plasma according to variation of. If omega is less than omega p, we get a negative value for dielectric constant, which leads to imaginary propagation constant. Hence, a plane wave in the medium which which decay exponentially with distance. It is not absorbed, but become evanescent, like a waveguide is cut off. A wave incident on a medium with this propagation would be totally reflect. When both frequencies are roughly equal, then the effective dielectric constant is 1. Practically, this happens at very high frequencies and above. The wavelet simply pass through the plasma without significant refraction. But there can be other effect, especially the plasma is magnetized by Earth's magnetic field and medium become anisotropic. Waves at these frequencies undergo Faraday rotation by the ionosphere, where their polarization vector is rotated as the wave passes through atmosphere. From these observations, we can observe two propagation mechanisms for wave entering the atmosphere. If it is below the Plasma frequency, it is simply reflected off. When it is above the Plasma frequency, the reflection analogous to that which occurs, atmospheric reflection occurs. Though it is much more pronounced because of large change in refractive index. In fact, provided the angle at which the wave enters the atmosphere is not too steep, the wave will be bent quite strongly as it enters atmosphere. And now, if the angle of incidence reaches total antenna reflection, the wave is reflected off the atmosphere is start to return to the earth, as we have already discussed. It is possible in the case of refraction that wave enters the atmosphere at too sharp angle such that the condition of total antenna reflection to occur. When the wave passes through the ionosphere and never return, there exists a minimum set of conditions on electron density, frequency, and angle of incidence. This figure shows a curved path of a reflected ray associated with frequency phi. The curved path reaches an altitude of height h once before being returned to Earth. If the incident and reflected rays are extrapolated at vertex, they meet at height that is called h0. This is called virtual reaction height of the atmospheric layer, by which you can send a signal from one place to another. You have from here you are sending the signal, and here it is reaching, and it is bending here due to atmosphere. The virtual height depends on conditions, the time of the day, and the layer being considered. It is shown here 200, 250 to 400 kilometer, daytime 250 to 250, 200, 250. But in night time, the F is about 300 and E is about 100. So in the daytime we have 4 and in the night time we have only 2. So we can conclude that multiple skips are possible by using reflection of Earth to establish multi-reflection process. And signal can propagate so much farther at night when D layer disappears, since it has a lowest virtual height. In general, the broadcaster can limit the range of the transmitter by controlling the power and manipulating angle of radiation. Pointing the antenna skyward reduces the angle of incidence. Thank you. In this lecture, you have learned about ionosphere, what is ionosphere, and how the ionosphere can be used for propagation. The just brief idea of different layers and how reflection occurs. Thank you.